Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And let's see, I see all kinds of questions here. I see a question from Brain. As a computer scientist and now physics student, I would love to ask what makes you think that our universe is an automaton, and how does it run if the medium is itself? All right, let's try and unpack that a bit. There's going to be a mixture of kind of science and philosophy. So what is science trying to do? Science is typically trying to make sort of abstract models of the world. So we're trying to say, we've got this thing in the world, and we want to be able to have a way of understanding that thing. We have some I don't know, some physical process that's happening of balls bouncing around or something like this. And we want to have some way that we can understand that by describing it in terms of momentum and laws about how momentum is conserved and things like this. We want to take the world as it is and turn it into something that we have a kind of a formalism, abstract way of describing that we can understand. So that's kind of the, in a sense, that's what science, natural science in particular, is in some sense trying to do. So now the question is, when we have the world, the universe, physics, whatever, how should we best describe that? What is the best way to take the world as it is and sort of turn it into something that we can understand? So back in antiquity, people would, ancient Greek times, a couple of thousand years ago and so on, people would just be saying, well, I think the world is made of atoms. Atoms are just these discrete things. Maybe they're in the shapes of polyhedra or something. I think that's what the world is made of. And somebody else would say, no, you're wrong. Actually, the world is flowing like water or something like this. And that's what it's fundamentally made of. For a long time, people didn't really have, that was kind of the way people were trying to think about sort of how the world was made up. And they would kind of argue philosophically, this is the reason things fall is because they like to be closer to the center of the earth, things like this. Well, then in the 1600s, kind of big idea that came out was the idea of using mathematics to describe the world, to say not that a rock likes to fall to the center of the earth, but rather there's a mathematical equation which can describe the position of the rock and how it changes with time as a result of being in the gravitational field of the earth. And that idea that you could describe the world using mathematical equations, you could say things like, the position is, a half times the acceleration times time squared plus whatever. The fact that you could write down a formula like that to describe the world, that was the big innovation of that time. Now, it's not that in figuring out its position, the rock is scratching its head, so to speak, and trying to work out, well, I'm at time 3.7, so I want to work out 3.7 squared, and that's where I should put myself. That's not what one imagines the rock is doing at all. Instead, it's just that that formula describes what physics has the rock doing. So it is a way of taking what physics is doing and transferring it to something that we can kind of understand in our minds. So that was sort of the tradition of making models in science for basically 300 years. And I suppose one of my contributions was in the beginning of the 1980s, really starting to think about, well, maybe there are other kinds of models one could make for the world, for nature. Maybe those models aren't in terms of kind of numbers and multiplication and calculus and those kinds of things. Maybe the models one should be making are models that are based on different kinds of rules. One would imagine that the world is determined, the behavior of the world is determined by rules of some kind. Otherwise, one wouldn't expect the behavior to kind of repeat itself and for us to have any kind of definite laws, definite predictability about what will happen. So there's some kind of laws, but we don't know what kind. And so I started thinking about kind of the more general kinds of rules that you can represent, for example, in a computer program. So one that I studied a lot, things called cellular automata, where you just have this line of cells, each one is either black or white, and then the rule just says for each cell how it should change at each step based on the colors of its neighbors. So very simple rule, a big discovery of mine from, well, 1981 to 83 or so, was even though the rules may be very simple, the actual behavior of the system may be very complicated. My sort of favorite example was what is called, I've called Rule 30. In some enumeration of these rules, it's the 30th one. And that particular one has the feature that even though the rule is really simple, started off from, let's say, one black cell, you get this very elaborate pattern. So then the kind of big meta discovery was very simple rules out in the sort of computational universe of all possible rules can show very complicated behavior. Kind of the guess was that that's sort of the secret that nature is using to make the kinds of complexity we see throughout nature. So in a sense, that idea that there are these very simple rules can produce very complicated behavior, that is a model of many kinds of things in nature, whether it's the growth of a leaf or whether it's something about the flow of a fluid or something like this. It's a model, just like mathematical equations are the kind of model that was initiated in the late 1600s. The idea of computational models kind of, I would say, seriously initiated in the 1980s through kind of my efforts, I suppose, was kind of an alternative way of thinking about models of the world. And in fact, it's been pretty cool that in the last, I don't know, 30 years or so, the vast majority of fundamentally new models made of things tend to be computational models, not mathematical equation kinds of models. So it's kind of 300 years of mathematical equations, and then over the last 30 years, kind of this transition to kind of computational models as the most common way of making sort of new models of things in the world. Models that were already made mathematically, you go on using those mathematical models, but models of new kinds of things tend to be made computationally. So it's kind of a significant kind of paradigm change in the way that models tend to work. So, okay, so then that's kind of just models of things where you take there's a thing out in nature, it does what it does, and you you're kind of making you're just using those models to kind of make this transform the things that are happening in nature to things that you can understand in your mind. Okay, so then there's a different level of this. The other level of this is to say, well, can we understand everything about how the universe works? Not just a model that captures certain features and allows us to take the things that we care about the shapes of snowflakes or something, and turn them into something we can understand in our minds. Can we do something much more ambitious? Can we make a model that is, in a sense, in every detail, reproduces what our universe does? So that at least in principle, we could run this model, we could find out everything. We could work out that here I'll be at this moment, 15 billion years after the beginning of the universe, sitting here yakking and trying to explain the universe, so to speak. That everything would emerge from the mechanics of this model. So I wasn't sure how that was going to work. I had a bunch of ideas along those lines in the early 1990s. And then starting about 5 years ago, we really made great progress in this and came to this thing called Wolfram Physics Project that is kind of an effort to really describe the full sort of machine code of the universe, to say sort of right down to the lowest level how the structure of the universe works. Now, this is sort of philosophically complicated, and there are several steps to this. But there's the question of, is it merely describing how the universe works? Or is it, in some sense, actually how the universe works? Sort of, is there, when we have an equation, a thing, a program that describes how something works, it's all well and good. It's a sort of a secondary thing. It's describing what's happening. But it's not actually, as people often say in this kind of philosophical direction, breathing fire into the equations. It's not sort of actualizing those things. It is merely saying, if this is what's happening in nature, we can describe it this way. So one of the interesting questions is, And by the way, when we're just sort of describing it in some way, people sometimes get confused. They say, oh, if the universe is supposed to be computational, what kind of computer is it running on? That's kind of a silly thing to say, because it's like saying if we describe sort of planets orbiting the sun that follow certain equations of celestial mechanics, what's solving the equations? Who's sitting there kind of with a quill pen solving the equations, so to speak? No, that's not the way to think about it. Those equations are merely a description of what nature does, and same with programs and so on. But it's a little bit different in the case of trying to understand sort of the full computational story of the universe. So this is a bit more challenging, and it's let me see if I can go there. This is a very deep rabbit hole, but let me see what I can do. And it all revolves around this thing that we call the ruliad, which kind of came up with, what was it, 2 years ago, maybe now? That is kind of a way to understand the structure of how this works. Just 1 second here. So it okay, so the ruliad. Well, let's talk about kind of computational model of physics. In a sense, what a computational model of physics would say is there is some rule that we could write down, we could sort of hold it in our hand, we can see it in our orphan language program or whatever. We've got this rule. If we run this rule long enough, we'll get everything that happens in the universe. Okay, so one of the things that's very mysterious about such a situation is, why did our universe get this rule and not another rule? In other words, it's kind of like, what's special? Our universe got rule number blah, blah, blah. Why did it get that rule and not another rule? It's kind of like, well, maybe there must be another universe somewhere that got another rule or something like that. Many universes, all with different rules. I don't think that's how it works. I think something much more, in a sense, bizarre is what's actually going on. I think what's really going on is that in some sense, all possible rules are being followed. So the way that that works is, if you have some sort of state of the universe represented as some kind of, you could represent it in some kind of computational way, and then you apply one rule to it, you apply a different rule to it. You make all these different paths of how different rules get applied. And sometimes two different rules that get applied end up producing the same state. So it's kind of like these two different rules go from one state to two different states, but then when you apply other rules, those two different states might merge to produce the same state in the end. So you get this complicated, entangled mess of kind of different paths of history corresponding to different ways to apply these rules. Well, the thing to think about is, well, what if we're applying all possible rules to all possible states? And what do we make by doing that? Well, we make this thing that we call the ruliad. And there are different ways to kind of represent that thing. You can think about it in terms of one kind of computational system or another. Doesn't really matter. There are different kinds of ways to sort of describe where you are in this ruliad. It's very much like saying, oh, I've got this coordinate system. I'm going to use latitude, longitude to describe, or something, position on the Earth, or I'm going to use some other thing that, different from latitude and longitude to describe my position on the Earth. There are different coordinate systems, effectively. There are different ways to describe where you are and what the details of what's going on in this ruliad object. But in the end, the ruliad is capturing all possible computations done to all possible states. Very complicated thing, but it has very definite structure. Well then, and here's where sort of we're hitting further down in the rabbit hole, the next thing to understand is, insofar as the ruliad represents everything, it represents also us. So we are, in a sense, observers of the ruliad within the ruliad. And so then the question is, well, what does a thing which is operating, whose mind is represented by all of these different computational processes happening inside the ruliad, what does such a mind perceive of the ruliad? You're kind of embedded there as part of the thing, and you are then perceiving other parts of the thing. What do you perceive? Okay, so a big result is that for observers with certain characteristics, it is inevitable that you must perceive that the things you perceive must follow certain laws. This is kind of a big result of mine of the last few years, has been that if you are a computationally bounded observer, you can only do a limited amount of computation in your mind, and you also are an observer who believes that they are persistent in time, even though they might be made from sort of different atoms of space or whatever at different successive moments of time. They believe that we believe that we have a sort of single thread of existence where I can remember my past. I sort of feel that I'm still me, even though I might be made of different stuff at every moment. Well, turns out those two features of us as observers imply that we must observe within this ruliad object certain characteristics of what we observe must have certain characteristics. In particular, it must have characteristics that correspond quite precisely to known laws of physics. It doesn't tell us all the laws of physics, but it tells us kind of the core laws of physics. Okay, so now the question is, we've got this situation where this abstract us in this abstract ruliad perceives the physics as physics does seem to us. So now the question is sort of, what is the reality of that? Is that just us making a model of what's going on, or is that in some sense actual reality? And the thing to realize is that in a sense there's, okay, in what sense does this ruliad thing exist? That's one obvious question. Is it just something we could make up and put in our computer? Or is there some fundamental existence that is independent of us happening to make it to write a certain computer program? Well, the point is there is a fundamental existence to the ruliad. And the reason for that is the same reason that in some sense there's a fundamental existence to some statement like 1 + 1 = 2. Once you have a definition of 1 and plus and equals and 2 and so on, then inevitably 1 + 1 = 2. That statement, in a sense, doesn't have any contingency. It's not a statement where you say, well, I might choose to write that down, I might not choose to write that down. It has an abstract sort of ideal existence, independent of whether I might choose to write it down with a pen on a piece of paper, or whether I represent it with rocks or something like this. It has an abstract essential existence. And the point is, the ruliad is the same way. The ruliad, in fact, is the unique object that is this entangled limit of all possible computations. There's not like, oh, there's this ruliad here and there's another ruliad there. It's using all possible computations. So in a sense, there's just one of it. And it is an inevitable thing. It is a thing that is abstractly must exist. It is once you have sort of the concept of computation, the ruliad is inevitable. So in a sense, it's inevitable that it exists. Now, it is not so trivial that an observer like us exists within the ruliad. That's something that you have to scientifically establish. And I've got some distance towards scientifically establishing that sort of observers like us can exist, maybe inevitably exist within the ruliad. But that's sort of a question of science once you have this sort of overall structure. But then the question of whether, so now the issue is, well, where is the fire, so to speak, in the quotes equations? Well, the thing is that this is all a necessary object. It is something abstractly necessary. It is something where there's no question of its existence. There's no question of its actualization, because it is inevitably abstractly exists. Now, the question is what? So for us, we're as elements of this thing that abstractly exists, we abstractly exist. Well, we feel that we not just abstractly exist, but actually physically exist. But what this is saying is, in this setup, there is sort of the looked at from the outside, one might say we abstractly exist. But felt from the inside, we're going to have the same experience that we have. We're going to have the experience that we choose to have of physically existing as well as abstractly existing, much as we choose to have the experience that we are persistent in time, even though we know perfectly well that, for example, we're made of different atoms of space, or on a longer time scale, there are, the cells of our body turn over and so on, but yet we still think it's the same us. So roughly the thing about is this, where does the reality come in? Where is the spark of reality? The spark of reality is, in a sense, that the ruliad is sort of this inevitable thing. The spark of reality, if there is one, is that observers like us are really there. Now, there's also the question, one of the sort of key features of this is to believe in reality, it should be the case that there's some stability to reality. My reality, my perceived reality, better be somewhat similar to your perceived reality, or it's hard for me to imagine that there's an objective reality that's not just something internal to me. And so one of the things about sort of reality, objective reality, and so on, is that we're all, if we think about our position in physical space, we're all very close by in physical space. We're all sitting on this one planet, or almost everybody at any given time is sitting on this one planet. Everybody's nearby, at least. And so our point of view about the universe is based purely on our experience of being on this one planet. If we were somewhere else in the universe, our experience of the universe would be quite different. So the fact that we have a common objective reality in terms of what's there in physical space, everybody knows, where Antarctica is or something. It's not, that's because we're all here on this one planet. It's that's one thing that kind of drives the existence of objective reality, is that closeness in physical space. Well, the same thing happens in the ruliad. We can think of different minds as being at different places in the ruliad. And so the thing that sort of drives objective reality there is that the minds, all of our minds, are nearby in the ruliad. The ruliad is very huge, and we can imagine, sort of vastly different kinds of minds in different places in the ruliad. And we can even see roughly how that works by doing computer experiments and just sort of jumping to some other place in the ruliad and seeing what's out there and realizing it's pretty different from what we're used to, but although it has some features in common. But so the thing that, in a sense, I view sort of the existence of objective reality, or our impression of objective reality, as a consequence of sort of the rulial flocking of minds like ours, that we're all pretty nearby in the ruliad. So we all kind of perceive the world in similar ways, which means that we can agree on some kind of objective reality. So anyway, I told you this was going to get a bit philosophical, but so in a sense, what we're saying is that the ruliad is everything. We are part of it, and it is, there isn't really let me address another issue, which is something running that makes the ruliad? Well, not really. It's like 1 + 1 = 2. You can say, I run with Wolfram language or something, 1 + 1, I generate 2. But in some sense, abstractly, 1 + 1 is always equal to 2. There's always that connection between sort of the left-hand side and the right-hand side. And the same thing is really true of the ruliad, that there is always a kind of the construction of the ruliad, from the very conception of it, it's kind of that already defines the whole thing. But the issue is that as computationally bounded observers of the ruliad, we don't get to kind of say, I can see the whole thing. We are forced to explore the ruliad kind of one small step at a time. And that is what leads us, in fact, to our notion of time itself, that we only go through these small steps. And that's what leads us to believe that sort of we're unfolding time as we kind of explore the ruliad kind of one step at a time, so to speak. And that's kind of, we're sort of this question of what is running. Well, the ruliad, we could view it as we're sitting here kind of being unchanged, and the ruliad is running around us. We're seeing the progression of different parts of the ruliad come into existence. Or we could say that the ruliad already is, and we are merely moving through the ruliad, and our internal computational processes are kind of moving us step by step through the ruliad. Either one of these is a way to think about it, but both ways, the fact that we have this bounded amount of computational capability relative to sort of the vastness of the computational capability of the ruliad, and that's why we're kind of seeing it one step at a time. And so you might say, well, what is it running on? What is the ruliad running on? Well, it's no more running on something than 1 + 1 = 2 is running on something. It is merely an abstract thing that necessarily has the form it has. All right, I think that's the end of my philosophy here. Let's see. I'm sure there are questions about this, so let me look at these. Max comments, does the universe have a halting probability or the ruliad? In other words, could the universe just stop? The ruliad won't just stop, because that is the nature. We can plainly see that there are computations that go on forever. But parts of the ruliad can stop. Parts of the physical universe can stop. The thing that is sort of characteristic of time stopping is, well, there are phenomena in physics where time stops. In particular, in black holes, time can stop. In particular, well, non-spinning black holes, Schwarzschild black holes that have so-called space-like singularities in them, they can have the feature that time effectively stops. And so in our models of physics, it's kind of like there's this giant network that represents the structure of space and everything in it, and you're progressively rewriting pieces of that network that represents the structure of space. And what can happen is that you simply stop being able to have rewrites that apply. It's kind of like, let's say you've got a mathematical expression and you've got 1 + 1 + 7 + whatever, and plus x plus y or something, and you keep on applying rules to reduce that mathematical expression. Eventually, you'll get to the point where the answer is 13 + 2x or something, and no more rules apply. It just stops. And that same thing can happen to the universe. It can happen to little pieces of the universe, and that's what leads to the singularities in the center of black holes, is there are these places where time stops. In the usual sort of treatment of this in general relativity, what one says is, oh, you got the spaceship and it's moving and it's going, and in a finite time as perceived by the spaceship, it will always end up in this singularity. Singularity is kind of a wimp out. Okay, if you have a mathematical theory that says we're describing everything by this curve, well, then it turns out somewhere that curve can't describe things. Let's say that curve was, oh, I don't know, the curve is always continuous, but yet something has to jump. Then you say, oh, if your model can only deal with making a curve that's continuous, then you say, oh, there's this singularity, there's this place where the curve isn't really defined. That's a singularity. What that really is, typically in physics, for example, it's a wimp out. It's saying the model really doesn't describe what happens at this particular place. So, for example, in a black hole, at the center of a black hole, not the event horizon, which kind of shields the black hole shields one on the outside from what's happening on the inside. At the singularity, at the center of a black hole, well, the simplest black hole just has a point singularity. Then what happens is that the equations of general relativity simply sort of say of themselves, we can't apply at this point. And so the way one thinks about it is one has this kind of smooth manifold that describes space-time, and you say, we're just going to punch a hole out of it. Where that hole comes from, how that hole works, the theory can't tell us, because the theory is all about just this smooth manifold of space-time. Now, in our models of physics, there isn't that issue. because space-time is made of something lower level. It's made of this network of all these atoms of space and the relations between them. And so there isn't the same thing of saying, oh, it's continuous space and then there's a hole punched out of it. It's just a feature of that network that has this thing where, for example, time ends. So it's so there are local places within the universe where time ends. Um, it is a feature of the ruliad that when time ends, time can sort of end in one branch, but there's always other branches. And actually, the existence of those other branches kind of relates to a bunch of paradoxes that have existed about black holes and quantum information and so on. Maybe, well, that will take us down another deep rabbit hole, but that's sort of related to this. But now, in terms of the universe as a whole, it's the universe as a whole, it will not halt. It could be the case that on one sort of branch, on one kind of quantum branch, the whole universe kind of turns into effectively a black hole. It kind of contracts on itself and so on. But there will always be other branches. And the question that you might ask is, an observer in that universe, what do they actually perceive? And, in other words, there's sort of a piece that collapses where time ends, but there's another piece where it doesn't. Well, let me describe another thing about sort of the future of the universe. One of the things that people started worrying about in the 1860s, actually, was the so-called heat death of the universe. So, the thing that is a general feature of physics, the so-called second law of thermodynamics, kind of says that even if you start things in a very orderly state with all the molecules in your object all carefully lined up, the tendency is for those molecules to get randomized. The tendency is for the molecules to be just bouncing around randomly, and that corresponds to heat. And so the thought has been that the universe will kind of run itself down, that all of the regularity of the universe will kind of dissipate into purely, quotes, random motion of molecules corresponding to heat. So that in the future of the universe, everything that we think is really cool about the universe and has a lot of dynamics and structure and so on, all of that will just turn into uniform heat. And that will be the fate of the universe. Well, the thing about that is this whole idea that things go from very orderly to seemingly random is a feature of the way that we're observing those things. Because the actuality is those molecules bounce around according to definite rules and so on, and those definite rules say where the molecules are going to be. Though, as far as those individual rules are concerned, there's nothing more random about the end state than about the beginning. It's just that in a sense, it's like encryption. You're running some encryption algorithm on the initial state, and it's ending up with that final state, which if you were able to be computationally sophisticated enough, you could decrypt that final state and say, oh, it comes from this initial state. But the key point is that observers like us don't have that level of computational capability. And so we end up kind of being forced to say, oh, we can't decrypt it. It just looks random to us. And sort of the implication is it just looks random to us. We can make nothing of it. It's kind of like it's featureless. It's contentless. But the actuality is those individual molecules are bouncing around in very particular ways that derive in a very specific way from that simple initial state. So in a sense, the randomness, the contentlessness of that state, of that final state, is a consequence of our feature as observers, and the fact that we're sort of not computationally sophisticated enough to see the real complexity in there. So for the universe, yes, in principle, many things will grind themselves down to being kind of heat-like. But heat is not boring. It's only boring to an observer who can't get inside it and sort of computationally work out what's going on. So in a sense, in the future of the universe, the heat death is only to observers like us. To observers different from us, capable of sensing individual molecules and doing more computations, it's like, wow, there's amazing things going on in this future universe. To us, it's like, oh, that just looks like a bunch of heat. To us, as we are today, it looks like, oh, that's a bunch of heat. The universe has run itself down. Well, so that feature of sort of the universe not getting boring, we have to sort of become more sophisticated as observers of the universe to find it not boring. Okay, so in this other possibility where there are these sort of situations in which the universe can just contract itself, time can stop, all those kinds of things. Time doesn't stop across all the possible branches of the ruliad. Time doesn't stop across all the possible paths of history, but it can stop on some of them. But the issue is, where are our minds? Are our minds spanning multiple paths of history, or are our minds stuck in a single path of history? Well, we already kind of know from our physics project that our minds span many paths of history. Just like when we observe molecules in a gas, we're not we're not looking at individual molecules. Excuse me. We're instead sort of at our scale, we're looking at large aggregates of molecules where we can say, oh, that whole collection of molecules looks like it's a fluid that's flowing and so on, rather than picking on individual molecules. It's the same kind of thing with respect to all these different branches of history, that our minds are effectively spanning many branches of history, and we're sort of averaging what happens on those different branches of history. So in a sense, this question of what the perception of a universe where part of it halted, what that will be like. Another part doesn't halt. And if the minds that exist at that time span these different branches of history, then those minds, I don't know how one will perceive that. I don't know it's hard to kind of imagine exactly what it will feel like, but but that's what one's dealing with. Now, to think about what it will feel like, we have to think about how our minds, in a sense, work. We come up with definite things. I'm going to say a definite next word, but yet somewhere in my brain, there are neurons firing that are probably thinking about a different next word. But yet in the end, a definite next word comes out. And in a sense, although it is not, we don't have a conscious awareness of that typically, there is this kind of sort of complicated consensus of things that's inevitably happening out of the 100 billion neurons of our brains. And so maybe that'll be kind of the way it would feel to a future observer critter, so to speak, that is kind of spanning many branches of history in the universe, where some of those branches do one thing and get boring and just time stops and other ones keep going. It's kind of like, well, I'm going to pay attention to the ones that are keeping going, and that will be my conscious thread of experience. That would be perhaps a guess for that. Let's see. Okay, there's many different interesting things here. So Andreas says, aren't we just describing our perception of the universe instead of the actual universe? What matters to us is our perception of the universe. This point that I was making, that there is a consensus objective reality, is sort of when we say, what's the actual universe? That's sort of what we tend to operationally mean by that. What we're saying with the ruliad, which has all these computational possibilities, we are not sampling the whole thing. We can't sample the whole thing. Just like we can't sample all of space. We're stuck in a particular place. Well, it's the same thing, that what matters to us is the description of the things that we can perceive. There are things that are far beyond what we can perceive. We might be able to abstractly reason about those things, but they're not our perception. And so, for example, laws of natural science tend to be about the things we can perceive. That's what we're interested in making laws of natural science about. So I think that there is an interesting question that one is going from the abstraction of the ruliad through to sort of the reality of physics, back to the abstraction of our perceptions. Yes, that is true. That's what we're talking about happening. And in some sense, one can shortcut that a bit by saying it is necessarily the case. We can go from the ruliad to certain kinds of perceptions that we have, that we describe in terms of laws of physics that seem to be kind of an objective reality. Formio asks, what would Kant say about the ruliad? Yeah, I think Kant would have a lot of fun with the ruliad. It's very difficult with philosophers. I've worked quite a lot on scientific history. I have tried to kind of also think about philosophical history. It's actually, in my experience, more difficult, at least for me, more difficult, because a philosopher like Kant, Immanuel Kant, what, late 1700s, early 1800s, if I remember my dates correctly, um, was um, kind of wrote a lot. Like I bought Kant's collected works. They fill a whole shelf. There's some parts that are more famous than others. But he thought about many things. He had ways of thinking about different things. I don't know whether I can abstract, as one often does in science, and say, it's this one law, it's this one principle. I don't know how to do that for Kant. And absent that, it's very hard for me to say, how does that plug into the kinds of things I'm talking about? Now, certainly, Kant had a lot of ideas about the noumenal, the phenomenal, all these kinds of things, the notion of what is perceived inside versus what's actually going on outside. He had the handicap that he didn't have the science to go around that, but I suspect many of his ideas resonate pretty well with what I'm talking about. I mean, I think there's a kind of a thread that goes from Leibniz to Kant, Leibniz from the late 1600s to Kant in the late 1700s, I guess, there's sort of a thread of philosophical thinking there. By the way, I noticed another question here from Fan asking, what's your view on atoms being capable of cognition and self-awareness in the brain by just assembling themselves? And that kind of resonates back to Leibniz, because Leibniz had this concept of monads. I have to say, for decades, I've tried to understand monads, and I've had a hard time. But for Leibniz, it's a very interesting thing that somebody pointed out to me recently. Leibniz didn't have the idea that kind of something like consciousness could arise from something that didn't have it. And so for him, even the smallest atoms had to have some version of consciousness. So his monads had consciousness. And that's that's sort of he didn't imagine that there was any kind of emergence of something different from something that from sort of simple beginnings could emerge something that was fundamentally not simple. That intuition that very simple programs, for example, can do very complicated things, that intuition, I mean, I'm sort of excited to have gotten that intuition in the early 1980s. I don't think that intuition was obvious. It certainly wasn't obvious to me. I mean, I didn't believe it to be the case until I actually did computer experiments, which kind of bashed me over the head with that fact. And certainly historically, people, in the early days of computers, people like John von Neumann certainly didn't have that intuition. Leibniz didn't have that intuition, I believe, and not even close. And so absent that intuition, you do kind of feel like if there is a property of the whole, it must somehow exist in its parts already, that there can't be a way in which the parts can have something that is not a property of them, but still a property of the whole. So this idea that sort of every atom must have this kind of this seed of things like consciousness and so on is something which happens if you don't understand that sort of computation can produce things that are beyond what the individual parts are sort of have what exists in the individual parts. So one of the things that's come out of science I've done is this thing I call the principle of computational equivalence, which says that it doesn't really matter what those parts are. The sort of emergent behavior, the computational sophistication of that behavior is equivalent, independent of what those parts are. If those parts are little black and white squares on a piece of paper, if those parts are neurons in our brains, if those parts are quarks in particle physics or whatever, it doesn't matter. That the kind of abstract computational capabilities of those things are the same, independent of the nature of the individual parts. Now, that's something we already know some about because we know that computers, it doesn't matter whether it's an Intel instruction set or an ARM instruction set, or whatever else, we can still ultimately run the same programs on our computers. We've got that that level of universality, and the thing that the principle of computational equivalence implies is that universality is vastly broader than that and applies across all these systems in nature, all these kinds of abstract systems, and so on. And so that kind of tells us that whether we're dealing with neurons or whether we're dealing with artificial neurons or bits or whatever else, we're still going to be able to construct something which has the same kind of overall characteristics. And so if you ask the question, is there in the brain, for example, is there this spark, this thing, this unknown thing from physics, this spark that gives us, for example, what we might think of as consciousness? Is there such a spark? Does there need to be such a spark? The whole point is there doesn't need to be such a spark. From elements that are themselves sort of elementary, that don't have certain kinds of properties, can emerge in the aggregate something which does have those properties. So I just don't think one needs those kinds of things. And by the way, with respect to actual human brains, we've got lots of evidence just in the last couple of years that we don't need extra stuff to get lots of capabilities of brains. I mean, one might have said, and people did, 5, 10, 20, 50 years ago, that if you want to get something that can write a coherent essay or whatever else, that's got to be a brain-like activity, and whatever magic there is in brains must be involved in that. But yet we know, post ChatGPT and so on, that actually it can just be bits and computation all the way down there. It is, by the way, interesting, just as a historical note, that even in the early 1960s, people were sort of imagining that that fact that you could kind of get the artificial intelligence like the human intelligence. They were imagining that back in that time. It took an extra 60 years to get from imagining to something closer to reality. Let's see. Eli comments, the ruliad contains its own encoding function and it is instantiated. The simpler the function, the better. So perhaps what you're saying is that if we are coming up with a description of what's going on, there are many possible descriptions we could come up with, and the simpler for our brains, for our minds, that we come up with, the better. So, describing the ruliad in terms of, it's a collection of possible Turing machines, or it's a collection of possible hypergraph rewriting systems, is much better than saying, for most of our minds, than saying, this thing that emerges in higher category theory and that is constructed by this huge tower of abstraction for our brains. I mean, for us, I kind of think the average human brain is more easily able to understand hypergraph rewriting than higher category theory. Might not be true of all, but it's certainly true of my brain. That the sort of the concreteness of saying this is how it works. And the same happened, by the way, in the early history of computing. I mean, back in 1920, this chap called Moses Schoenfinkel had invented these things called combinators, which, as we now know, are completely capable of doing any computation you want to do. But they are very hard to understand. And even today, they're kind of I wrote a book about combinators a few years ago. They're really a brain twister. And then came lambda calculus and recursive functions. These were also not quite as brain twisty as combinators, but hard to understand. And then came Turing machines, which are in a sense very direct, very mechanical. And that was when people began to understand sort of the abstract idea of computation. So there's great value in having sort of the simpler basis for thinking about things, even if that basis still lets you talk about the same thing as these other ways to talk about it. Let's see. Gosh, let me look some more. I'm sorry, there are many interesting questions here, and I'm just trying to pick out ones that follow what I've already been talking about, and then we'll maybe cover some others. Hussein asks, can we look at free will as probability distributions in the ruliad? What happens in the ruliad during overlap of two free wills? So I think the way to think about free will is this. To say that one has free will, one of the features of that is it's not possible to predict what we'll do. We're just doing what we do. It's not like you can say from the outside, oh, I know this person's going to do that. I know this particular moth is going to sort of run itself against the window because it sees the light type thing. Then one could say that doesn't have free will. There's something mechanical inside that's making it do that. But on the other hand, if you look at the person, the thing, and it is behaving in such a way that you can't readily predict what it will do. The only way to find out what it will do is sort of to be it, or to run a computation that's just the same as the one that's running in it. That's the way that you end up with what appears to be free will. It is not something where it is determined by the outside. It is something that is intrinsic to the system itself. It just does what it does. It computes what it computes, and out of it comes whatever behavior comes. Now, we're used to ourselves feeling that we have free will, and part of the reason we feel we have free will is because we can't readily foresee what we're going to do. If we could always say, I know I'm going to do this, then we wouldn't think of ourselves as having free will. It's that we are thinking, and we can think about thinking, but we're still, that never happens faster than the thinking, so to speak. Or when it does, we don't say we have free will about those kinds of things. And by the way, whenever we say, I did it because of something that I learned here or there, that's a way of saying, of making being able to sort of jump ahead, to not have to think it through as we think it through. And we only feel that we have free will when we think it through as we think it through, so to speak. We're not the only things that we should, I think, attribute free will to. There are many. This principle of computational equivalence that I mentioned says that there are lots of systems that are as computationally capable as we are. And all of those, in a sense, we can think of as having free will, in the sense that we can follow their steps of computation, but we can't jump ahead and say what will happen. I mean, a famous thing people say is, the weather has a mind of its own. But why do they say that? They say that because they can't readily say, I know what the weather's going to do. The weather, one feels, is just going to figure it out for itself. And the way it figures it out is by all these processes in the atmosphere and so on. It's not electrical activity in a clump of neurons. It's something different. It's a different substrate, but it's the same idea. And it's the same kind of notion of kind of, it is seeing what it will do by doing it, so to speak. And that's sort of, I think, the essence of free will. Now, the principle of computational equivalence says you don't get to have two different incompatible free wills, in the sense that it isn't the case that if sort of something is computationally as sophisticated as it can be, it's not like there's only one scale, there's only one place where you get to. Everything is equivalent. It's not that you have sort of A is free will with respect to B, which isn't free will with respect to C, and so on. You can have things like that when you're kind of at a lower level of computational ability, when you say, can this very simple sort of mathematical principle, can you find this closed form solution in of this type to this problem or not? That's kind of a below the level of sort of computational equivalence. But the things that we think about, like minds, are always at that level of computational equivalence. So this notion of free will is kind of ubiquitous for those kinds of things. Let's see. Okay, question from Technic here. What runs the ruliad? I've been talking about this, and I know it's a very brain-twisting kind of issue. It says, computers run programs, mathematicians do thinking right on paper. In every case, for the information to be processed, there has to be some sort of processor doing the work. What's the equivalent for the ruliad? If there isn't intelligence running it, why does it follow rules? Well, that was what I was trying to explain earlier. It is an abstract thing. It is not that, as I'm saying, 1 + 1 = 2 is true independent of whether you write it on paper, do it with rocks, think it in your mind. it is an abstract thing. And that's what the ruliad is. But in a sense, we are abstract too, as entities embedded within the ruliad. And as I was trying to explain before, that's kind of, it is this abstraction that is sort of inevitable thing that exists abstractly, that is what is, there isn't a sense of running the ruliad in any more than there is a sense of running 1 + 1 to get 2, so to speak. This is a difficult concept. And it's a concept that, in a sense, I've sort of gradually gotten more to terms with this concept. Although I have to say, as one thinks about it in one's own existence, and one thinks about kind of, it is, one can think about it abstractly, kind of dispassionately, but when you try and live it, it is a strange thing to say, what I'm doing is ultimately determined by this whole computational process and so on, and it's all a part of this process. And I have to say, the sort of the ultimate abstraction of it all, and is somehow at odds with my own personal perception of the world's real. People are out there. They've got other minds that are like my mind, and so on. It's a funny thing, but it is a thing where one realizes that in this kind of infinite abstraction, there is the thing that is somehow significant about us is our kind of coherent individual existence. That it isn't the case that we say there could be a better me somewhere out there that is bigger, captures more of the ruliad and so on. As you do that, there is sort of less coherent existence. So in a sense, the importance of us, the thing we have, is our coherent existence, with all its specialness, with all its particularness, with all its non-standardness with respect to the ruliad. And so, I kind of feel like, as one thinks about that, it's kind of like one knows that abstractly, one knows one's just made of a bunch of, atoms that have certain chemical properties and this, that, and the other. But that doesn't really detract from one feeling what one feels internally, so to speak. It's interesting for me, at least, to try to imagine, what does it feel like to be a computer, so to speak? And is it something where, in a sense, one could imagine sort of feeling like that, just as one can imagine feeling like a different person, a different mind, so to speak. And it's sort of an interesting and brain twisting thing to try and think through. Let's see. Tech is asking, what if the observer is a computational system? The observer absolutely is a computational system. We are computational systems. And we are computational systems with certain particular characteristics. If the observer was an AI with sensors all over the world and so on, it would have a very different it would form very different theories for how the world works. For example, just not being, the notion of space might be different if the sensory inputs are from sort of internet nodes, so to speak. The concept that there is this idea of space where things are sort of together in space and there's a certain geometry to it, one wouldn't necessarily have that. That's a feature of our sensory apparatus perceiving the world. And I think this whole question about sort of what are observers like, I have this whole effort that I call observer theory, which is an attempt to sort of formalize what an observer actually is. Just like we can formalize to some extent what a computer actually is, that we have these computational steps, these rules that a computer follows to run from one state to the next. What observers fundamentally do is they equivalence many different things. So an observer, there's lots of complexity in the world. There are all these pixels falling on my retina all these photons falling on my retina at this moment. But what I form from that is an impression that I'm looking at this camera, and so on. It's not, oh, I'm thinking about every photon that falls on my retina. So what I'm doing as an observer is I'm equivalencing together all those different configurations that the photons could have fallen on my retina, and I'm saying all I care about is there's this camera in my field of view. So that is the characteristic feature of observers. They're taking the complexity of the world and saying all these different detailed sort of things, configurations of the world, they're all equivalent. And what I care about is some aggregated feature of the world that is sort of that I can summarize simply enough to kind of stuff it in my finite mind. So observers are taking the complexity of the world and compressing it to the point where it fits in finite minds. And that's kind of the characteristics of observers. And that is implemented ultimately by computational processes. But the sort of the import of those processes is this equivalencing kind of idea. Those processes do things like say, well, for example, for a brain, they're like taking all of those different nerve signals and concluding that the consensus result is, gesture with my hand like this. Even though different neurons in my brain might be sort of implying different kinds of behavior, there's sort of a consensus achieved. And that's kind of like what observers are doing, sort of achieving consensus. One can generalize that in ways I don't fully understand yet, but one can generalize that to sort of the will of society and things like this. The kind of how are things formed where one is kind of going from all these individual parts to some sort of equivalence thing where in the end everybody just goes and does that thing. And as opposed to all the individual pieces doing what they're individually doing, sort of on a large scale, you conclude society or a brain or something is doing this. And that's kind of something like an active observation. Let's see. Eli is commenting, maybe each species of observer conflates all their threads into a different identity mapping of the ruliad. Each species' encoding function is a distinct identity, speciation's blueprint. That's an interesting idea. I mean, I think that this, at some small level, it's true of individual people, that sort of one's way of understanding things, all of us have a slightly different way of understanding things. It may be close enough that we can communicate with words and so on, but in the end, the sort of engram of our understanding in terms of neurons will be different. And one could ask the question, if you look at, the cats and dogs and whales and dolphins and cockatoos and who knows what else, whether there is a characteristically different sort of form of understanding that exists in all of those critters. And that's an interesting idea. Be interesting to try to characterize that. Let's see, maybe one or two other things here. It's a question from Arnold. Can you explain what infinity is? Oh, I'm seeing just a comment from RY here. Perhaps you should replace school grades with extent to which you have captured the ruliad. Yeah, it's the way to think about this is sort of a mind is at a particular place in the ruliad. In a sense, as you understand more, you are encompassing more of the ruliad. As we invent a new paradigm for thinking about things, we're kind of colonizing more of the ruliad. So yes, there is a sense in which when you only understand this one set of things, this one way of thinking, you're in a much smaller region of the ruliad. And as you expand your thinking, so to speak, you quite literally expand in the ruliad. So that's kind of a fun way to think about it. And I do think that one day we will have sort of a somewhat quantitative way of explaining these two minds, human minds, let's say, are sort of this distance apart in rulial space. These minds with these different educational backgrounds are this far apart. These other minds are this far apart. Similarly, we'll have the human minds are, distances up to 10 apart, let's say, but then we'll have the cockatoo, which is distance 1,000 away, and so on. And we'll have ways to quantify that kind of distance in rulial space. It's a similar thing I've tried actually without success so far to sort of characterize that for things like computer languages. How far apart are these languages? One could imagine for human languages as well. We have this kind of illusion, perhaps, that human languages all describe the same concepts, that there's a universality of translation between human languages. But yet people who deeply know languages will tend to say that's not true. There are concepts that are only expressible in French or something that don't really have a translation because they are enmeshed with the culture that goes around that language and so on. And that's kind of a further distance in rulal space. So it's an interesting thing to think through. Well, let's see, one thing here. Let's Arnold is asking, can you explain what infinity is? Well, infinity at the beginning is a simple concept, but when you start digging into it, it's not so simple. So there are various ways to get to infinity. We can say, imagine we just have more and more things. We just keep going. And like every moment, we add another thing. We add another grain of sand, whatever else. And let's imagine that we just go on adding grains of sand forever. How many grains of sand do we have after we've gone on forever? Well, we have an infinite number of grains of sand. Of course, we have to have a notion of going on forever. I mean, somewhere we have to have this way of just sort of extending out to infinity, so to speak. We imagine it for whole numbers, 1, 2, 3, 4, 5, etc. Just keep on counting. Just keep on going. We have this operation that says get the successor of a number. Just keep on going, never stop. Where do we get to? Where do we get to if we never stop? Well, we have this notion, we call it infinity, which is where we get to if we never stop. Now, in fact, there's a finer gradation of that for integers, for example. It's in the theory of transfinite numbers from the late 1800s. There's kind of this notion that we name the thing we get to if we just keep counting forever. We call it omega. And then we can ask, well, we kept counting forever. We got this thing called omega. Let's just do one more step. Then we have omega plus 1. Then let's do omega more steps. Then we have 2 omega. Let's do that omega-ish times. Then we have omega times omega, or omega to the power omega. And we can, once we have kind of a concrete thing that we can pick up and say, this is the result of doing all this infinite stuff, then we can start reasoning in terms of that infinite object. But normally, we are very coarse about our infinity. I mean, in Wolfram language, for example, it is perfectly adequate to just have a symbol called infinity. So it has properties like 1 over infinity is 0. Infinity, let's say infinity minus infinity is, well, infinity plus 1 is still infinity. Infinity minus infinity, I think that is considered to be indeterminate. Certainly infinity divided by infinity is considered to be indeterminate. You don't know what its value is. And how could you know what its value was? Well, if you knew where those infinities came from, if they both came from a quantity x, and that quantity x is being slid out to larger and larger values, and what you're computing was x over x, then for all x, x over x is equal to 1. It's just a mistake to say, let's replace those x's by the result of sliding them out to infinity and replace them both by infinity. Once they're both replaced by infinity, we have no idea what that means. One of them could have been an x squared instead of an x. It would still be represented as infinity. So we're in a sense being forced to say more about the process by which we got to things to be able to work carefully with infinity. And it's the same thing with these transfinite numbers that I mentioned. We have to know we got to omega by going 1 plus 2, going 1, 2, 3, 4, 5, and counting up to infinity. Curiously, in the theory of transfinite numbers, there are transfinite ordinals, which is the thing I just described, numbers in order. There's a different concept of so-called transfinite cardinals, which are just like you're putting more and more things into a collection, not you're in sequence going thing to the next thing, to the next thing, to the next thing. But you're just saying, let me make this bigger and bigger bag of things. And the infinity there, the sort of lowest infinity there, is called Aleph 0. And that's the number of integers that exist. Omega is the integer you get to by counting forever and not stopping. Then the integer you get to is omega. But if you just say how many integers are there, you might say those two concepts are the same, but they're not. When you start thinking about the process by which you get there, those concepts are not the same. And those are distinguished in the theory of transfinite numbers. And that's sort of an important concept there. But when it comes to the notion of infinity, some of the time you can just say, I've got this thing, it's called infinity, and I can reason in terms of this thing called infinity. One place where that doesn't work is when you're thinking about infinite processes. And it's the same thing as what I've just been describing. A lot of the time, it's not good enough to just say, I've got an infinity. You've got to say something about the process by which you made that infinity. And in computation, there's a certain rigidity to this notion of an infinite computation, having this process go an infinite number of steps. In the case of sort of theories of computation, you can say, well, I'm just going to say I'm just going to write down the answer. Let me call it, O or something, being the answer to what I get when I run an infinite computation. I'm just going to name it. I'm going to call it O, like I was describing for these integers. You call it omega, you call it LF0, and so on. Well, the problem with that is there's not a lot you can say about it. You say, well, I've got O from this computation. Well, actually, I've got another computation. I have no idea whether that other computation, again, an infinite computation, is giving that same O, or whether it's giving something completely different, a different O. You can't even tell whether they're the same. And for example, for transfinite numbers, there are particular cases where you can find that they're the same. There are other cases where you cannot find that they're the same, and so on. So it's kind of this idea of, well, we just state this thing called infinity is something which, in simple cases, you can get away with that. But when you start digging in more deeply, you have to kind of say the process by which you got to that infinity. You can't get away from that. And in a sense, the infinity is trying to package up a lot of process, an infinite amount of process. But when you start trying to understand what that infinity means, you have to unpack that process. So, for example, in terms of the universe, there are questions like, is the universe in any sense infinite? Well, in our models of physics, it's not. Simple as that. It's just not infinite. Well, in some sense, it's not. It's only infinite in the sense that 1 plus 2 plus 3 plus 1, 2, 3, 4, 5, that you can go on sort of getting another number forever. In that sense, the universe is infinite. That in that sense, you can keep running it. The ruliad has all these different consequences of different computations, and they keep going, so to speak. But in some sense, there's no packaging of infinity in the universe. There's nothing where we say, I pick this thing up and it's infinite. There's a process that goes on that keeps going, but there isn't something where we say, I point at that thing and it's infinite. I point into the night sky and I say, there's an infinite distance that I'm seeing out there in the universe. There isn't. So I think there's sort of a way in which one can talk about abstractly about the infinite, but when it comes to kind of reasoning about it, you have to unpack it into the process by which you got to that infinity. Now, this shows up in both computation and in thinking about physics and so on. When you have computers, you can say one of the questions that is not finitely answerable for any computer in general is, what will that computer do after an infinite time? Will the computer keep running, or will it halt, for example? If you say, will that ever happen, even after an arbitrarily long time? You can't answer that in general with a finite computation. But you could imagine a computer, a so-called hypercomputer with a so-called oracle, where the hypercomputer just knows the answer. We don't know how to build the hypercomputer, but we imagine it exists. And then you can sort of start asking for hypercomputers and hypercomputers of hypercomputers and so on. There's this whole hierarchy, a whole infinite hierarchy of sort of hyper things, or oracles for oracles, and so on. And it's sort of the same thing with the universe and the ruliad. We're talking about the ruliad, but there is a hyper-ruliad in which those things which are infinite for the ruliad, the hyper-ruliad just knows in a jiffy, so to speak. And so, well, why don't we think about the hyper-ruliad? The main reason is that the ruliad, there's no connection, there's no causal connection. There's an event horizon that separates the ruliad from the hyper-ruliad. Whatever happens in the ruliad, it's kind of like Vegas or something, stays in the ruliad. There's no communication between the ruliad and the hyper-ruliad. By the way, it's the exact same phenomenon with black holes. Black holes are what one might call hypo. They're signs of a so-called, what one could think of as a hypo-ruliad, a sub-ruliad, where instead of computations going for arbitrarily long, as they do in the ruliad, in a black hole, the computations terminate after limited time. So they are doing a lower level of computation. They're doing things which are sort of more finite than the things that happen in the ruliad. And that's sort of why there's this event horizon that separates those pieces of hypo-ruliad from the usual ruliad. And by the way, just to make it even more sort of rabbit holed, so to speak, I think there's a sort of principle of rulial relativity that one can imagine, where as an observer in the ruliad, where you're made up of things that are from the ruliad, you observe certain things. You could be in the hyperruliad, and then you would be more capable as an observer. You would be a hyperrulial observer observing the hyperruliad. And I suspect that there is a rulial relativity that says that the things that you will observe as a hyper observer in a hyperruliad are just the same as the things that you will observe as an observer, an ordinary observer in the ordinary ruliad. So that's a little bit about infinity here. It's okay, many other comments and questions here, but I think I have to go back to my day job. But thank you for asking these let's see. Yeah, thanks for asking all these interesting questions. I see more questions here, and which I'd love to answer, but I have a day job. We're making new versions of Wolfram language, and I got to work on some aspects of that. And I hope we're going to have a great new software release and a very interesting new product coming out soon. My effort is to take all the things I try to think about and make use of them in trying to build the best, most useful, most generally interesting software we can. And that's kind of that's the day job. And I kind of think that when one thinks about making the kind of general sort of full-scale computational language that I've spent the last few decades making, that turns out that to actually do that, you actually do end up having to understand lots of these pretty abstract, pretty elaborate, deep philosophical kinds of questions. And so it's very synergistic for me to think about these kinds of things alongside the practicality of building our computational language. But anyway, I got to go do my day job and build computational language, and hope to make something that is practically useful as well as conceptually embodying lots of the things that we end up having a chance to talk about here and so on. All right, with that, I look forward to chatting with you another time. Bye for now.